Explain generator with the power electronic interfaces. So in the heading only it is there, generator with the power electronic interfaces. So we in this is in which model it is coming? Fifth model. It is related to what? It is related to the power electronic power quality disturbances. Okay, so here first we shall get to know that generator with the power electronic interfaces. So here first we consider for sinusoidal pulse width modulation. So we use inverters, okay, converters. In power electronic interface means we get inverters, converters, right, harmonic filters we get. So first here we can write it like this: pulse width modulation and HVD. For that 29 and 31. That means for sinusoidal pulse width modulation, harmonic voltage distortion is highest at order of what? At order 29 and 31. That is a close to the switching frequency. So first pulse width modulation, the harmonic voltage distortion is 29 and 31. Next what we write in the sentence is wind turbine. Okay, so distributed generation subject we are reading. So in that either we get wind turbine or we get a solar, right? So here generator with the power electronic interface. So first we shall see the wind turbine first. Okay, wind turbine with the power electronic converter, because we need a converter in order to convert, right? So either AC to DC or DC to AC. So we need a converter. So wind turbine with the power electronic converter, current distortion, how much distortion? It is 1.6% at fifth harmonic. Okay, so 1.6% at fifth harmonic and 0.6 at seventh harmonic. 1.6 for fifth and 0.6 for seventh, and for other harmonics it is below 0.2%. okay, so first we have discussed about solar. Next wind we have discussed. Next is solar power installation. We know a solar cell, right? So here measurement of the harmonic emission due to the solar power installation, about what? About how much you will get? 37 and 101 kilowatt we have considered. That example we have considered. Harmonics adder, how much you will get here? Harmonics adder is 3 and 5. Okay, 3 and 5. Rated current is 2%. Okay, so for the third and fifth harmonic, rated percentage how much it is? Around 2%. You can observe here for fifth harmonic how much we got? 1.6, right? So for the third and fifth, around 2% rated current you'll get. That is for the solar. And total harmonic distortion is 3.5%. Next here it is a harmonic distortion of an inverter that is expected to be typical for future PV or microgeneration installation. When it comes to the inverter, so second harmonic, okay, so second harmonic it is 3%. So here 3 5, it is 2% rated current. Okay, here second harmonic it is 3%. Okay, and 357 around 1.5% for the inverter it is. Okay, for the inverter 357th harmonic 1.5% rated current, and for the ninth harmonic it is below 1%. So remember like this. For the fifth and seventh harmonic what we have written? For the wind 1.6 and 0.6, right? So similarly for the 357 it is around the 1.5%, and below ninth harmonic below 1%. Okay, next the coupling between the two sides of the converter. Here we coupling between the two sides of the converter is strongest for cycloconverters, but even two converters are connected via DC link will transfer frequency components. So we have a two converters, okay, we have a two converters and we have a DC link here, and DC link will transfer the harmonics, okay. Resonance in the DC link may even amplify certain interharmonic frequency. So what happens, resonance in the DC link, that will also reduce or that will also even amplify certain interharmonics frequencies. Considering a 6 pulse here, considering a 6 pulse input as well as output stage result in a spectrum with the following frequencies being present, that is f equal to, what we can write is 6m plus or minus 1 f in plus or minus 6n f out, okay. So 6m plus or minus 1 input, frequency input, plus or minus 6n f output. F in means grid frequency, f out means non-grid frequency, okay. And n is a 0 1 2 3 and m is a 1 2. It will not start from 0 because 6 into 0 it will become 0 plus or minus 1. So that's why m will start from 1 2 and n will start from 0 1 2, okay. So there are indications that active power electronic converters generate more of continuous spectrum than the existing power electronic converters. So there are indications, okay, there are indications that active power electronic converters generate more of the continuous spectrum than the existing power electronic converters. So remember like this, AP, EC and EPEC, okay, APEC and EPEC. So it will generate more continuous spectrum than the existing this one. It will generate more spectrum than the existing power electronic converters. So that will lead to what? That will lead to more interharmonics and increased risk of high distortion due to the resonance. So here, because active power electronics will generate more than the existing power electronic converters, so that will lead to what? That will lead to the more interharmonics and it will increase the risk of high distortion due to what? Due to the resonance. So here, that is, certain types of power electronic converters may amplify interharmonics that are present in the voltage at the converter terminals. So we have some type of power electronic converters which will amplify the interharmonics that are present in the voltage at the converter levels, okay. So we have already came to know that DC link may even amplify certain interharmonics. Like that, we have some power electronic converters also which will amplify the interharmonics, okay. So a well-known effect of interharmonics voltage component is that they result in a modulation of the voltage amplitude, which in turn may lead to a light flicker, okay. So a well-known effect of an interharmonic voltage component is that will result in a modulation of the voltage magnitude, okay. So that, which in turn may lead to what? Which in turn may lead to the light flicker.